Hi everybody, I'm Guoli from University of Science and Technology of China. I'm going to present the work DMTree towards efficient tree indexing on disaggregated memory via compute-side collaborative design. Disaggregated memory decouples compute and memory resources into separate resource pools, where the compute pool handles request processing and the memory pool stores index and data. This disaggregated architecture ensures high resource utilization and high resource scalability. Compute and memory servers connected via high-speed network. And cross-network communication in disaggregated architectures, index is a key component to accelerate data access. Existing tree-based indexes in disaggregated memory include B+ trees and adaptive radix trees. In disaggregated memory, the index is stored on the memory server, and the compute servers access it remotely over the network, traversing the multi-level tree from the root to the leaf node to retrieve data. The commonly used inter-server communication technique in disaggregated memory is RDMA. RDMA provides two types of primitives, one-sided and two-sided. Due to the characteristic of one-sided operations, which allow remote data access by passing the memory server's CPU, they're widely used in disaggregated memory applications. In RDMA communication, the RDMA exposes two key resource bottlenecks. The IOPS resource bottleneck, which limits how many operations it can process per second, and the bandwidth resource bottlenecks, which limits the data transfer rate. Building on this background, the key challenge for indexing in disaggregated memory is to mitigate cross-network overhead and the network resource bottlenecks and the heavy client concurrency, which is also critical to improving the overall system performance. Existing works mitigate cross-network overhead by caching upper-level tree on compute servers and fetching only the leaf nodes remotely, thereby reducing most cross-network accesses. However, remote leaf node accesses still face fundamental trade-offs in RDMA resource utilization. Based on index type and the resulting RDMA network bottlenecks, existing index can be divided into two categories: contiguous range storage and precise key-value locating. First, for index with contiguous range storage, such as B+ tree or long indexes, they use coarse-grained leaf nodes, where each leaf node stores a contiguous range of key-value entrants. During key-value request, the compute server roughly locates the target leaf node and then remotely reads the entire node from the memory server. The coarse-grained reads called reunification, wasting bandwidth and leading to bottlenecks due to insufficient bandwidth resources, especially during search operations. Second, for indexes with precise key-value locating, such as adaptive radix trees, they use fine-grained leaf nodes to precisely locate the request key-value entrant. This design avoids reunification and is therefore bandwidth-friendly. However, the fine-grained nodes increase RDMA request. As the leaf node stored separately, it introduces extra RDMA for reading separated leaf nodes during scan operations and for updating upper-level trees during insert operations. The fine-grained nodes increase RDMA request, consuming IOPS and leading to bottlenecks due to insufficient IOPS resources, especially during insert and scan operations. In conclusion, existing works face trade-offs in RDMA network resource utilization and fail to achieve consistently high performance across different index operations. The question is that how can we balance the inevitable resource consumption and achieve consistently high performance? From existing works, we observed that in disaggregated architectures, index access patterns route all requests from the compute server to the memory server. And the heavy concurrent accesses from the compute-side clients, RDMA traffic converges at the memory side, causing memory-side RDMA resources to become the bottleneck. Meanwhile, the compute-side RDMA resources remain underutilized. This provides an opportunity to break the RDMA resource utilization dilemma. Our main idea is to leverage compute-side RDMA to offload the inevitable index operations that are aggregated at the memory side. We propose a compute-side collaborative design and an index optimized for disaggregated memory called DMTree. The compute-side collaborative design includes, first, offloading precise key-value locating to the compute side. Second, introducing compute-side collaborative cache. Third, offloading concurrent locking to the compute side. Next, we will go through the key design of DMTree in detail, step by step. In DMTree, we adopt a B-tree-like structure, in which leaf nodes store key-value entrants, while internal nodes are used to locate target leaf. Additionally, each leaf node is augmented with a fingerprint table, where each fingerprint is generated by hashing the key and is used to precisely locate the target key. When processing the request, the system first locates target leaf and its corresponding fingerprint table. It then traverses the fingerprints to identify the target key and reads only the corresponding key-value entrant. This approach avoids fetching the entire leaf node, thereby reducing bandwidth consumption, but obviously it incurs additional RDMA requests for key-value locating. In our compute-side collaborative design, we offload the precise key-value locating to the compute side to leverage and utilize the RDMA resources across compute servers. Specifically, instead of storing fingerprint tables on memory servers, we scatter the fingerprint tables of different leaf nodes across multiple compute servers using a distributed placement policy, such as round-robin or consistent hashing. To retrieve a fingerprint table, we store its address as an additional pointer in each entrant of the internal tree nodes. When processing a key-value request, the system first retrieves the fingerprint pointer from the internal tree. Then it fetches the fingerprint table across compute servers. By matching against the fingerprints, it precisely locates target key and finally retrieves the corresponding key-value entrant from the memory server. By offloading precise key-value locating to the compute side, DMTree avoids fingerprint-related RDMA requests from being concentrated on the memory server, thereby alleviating the memory side IOPS bottleneck. Built on compute-side fingerprint storage, DMTree introduces a compute-side collaborative cache. Each fingerprint table is primarily stored on one compute server and can be cached on other servers, minimizing remote accesses and accelerating compute-side fingerprint lookups. The primary fingerprint table is updated in real time, while cached replicates are refreshed asynchronously. With the compute-side collaborative cache, we accelerate fingerprint access, but we also need to handle consistency issues between cached fingerprints and remote storage. For example, we may see cache misses due to outdated fingerprint cache entrants, as well as mismatch triggered by tree node splits. First, to handle fingerprint misses caused by outdated caches, we use the primary fingerprint table stored in the internal tree to fetch the up-to-date primary fingerprint table and refresh the local cache accordingly whenever a miss occurs. Second, to handle fingerprint mismatches caused by tree node split and asynchronized fingerprint caches, we add a version field to each of internal node entrant, leaf node entrant, and fingerprint table. A leaf node split updates the version only in primary storage. Therefore, if the cached version fields do not match those in the primary storage, it indicates that the primary tree node has been split, but the cache had not been updated. The compute server will then refresh the corresponding cache. The compute-side collaborative cache further accelerates fingerprint access across compute servers, with consistency ensured through validation fails. To further extend the compute-side collaborative design, we distribute the log fields of leaf nodes across compute servers, similar to the distribution fingerprint storage, offloading concurrent locking operations to the compute side. This approach avoids RDMA requests for locking from being concentrated on the memory server and further alleviates the memory side IOPS bottleneck. We also introduce other RDMA resource optimizations enabled by the compute-side collaborative design. For example, using the compute-side fingerprint table to filter out empty key-value slots within leaf nodes during scan operations, preventing boundless wastage. Further details can be found in the paper. For evaluation, we run experiments on 7-node cluster, consisting of 6 compute servers and 1 memory server. We evaluate DMTree using YSB workloads and both uniform and zip-file key distributions, covering macro benchmarks and YSB workloads. We compare our DMTree prototype against representative disaggregated indexing baselines as shown on slides. This figure shows the throughput of DMTree compared to existing works and macro benchmarks with varying numbers of client threads. Under these macro benchmarks, DMTree outperforms the baselines across search, insert, update, scan operations, and heavy client concurrency, improving overall performance by up to 5.7 times. This figure shows the throughput of DMTree compared to existing works and YSB workloads. Under YSB workloads, DMTree consistently outperforms existing disaggregated memory range indexes, delivering better overall performance. We also evaluate the effectiveness of the design techniques and performance. By leveraging RDMA resources across compute servers and with the compute-side collaborative design, DMTree mitigates memory-side bottlenecks and improving the overall indexing performance. To conclude, we propose DMTree, an efficient tree index for disaggregated memory through compute-side collaborative design, including designs offloading precise key value locating, compute-side collaborative cache, and offloading current locking operations. For detailed results and analysis, please refer to the final paper. Our code is open sourced and available on our project website. And for artifacts evaluation, please refer to the following website. Thank you. I'd like to take your questions and comments.